Alright, so after a long time of doing rectangles and limits of sums and all that kind of thing, we're actually going to go back and we're going to use those rules for the antiderivatives that we found earlier and start applying them to actually help us find these areas in a much, much simpler way. Okay? And that brings us to the fundamental theorem of calculus. Okay? Now, let's examine what this is, and then we will do all three of these in a much, much simpler way. Okay? So, notice here the notation. We've used that capital F to represent the antiderivative before. Okay? So, if capital F is the antiderivative of F, then the integral from a to b of f of x dx is capital F of x, and then you have this notation here. We have the bracket. Sometimes we won't even write the left side of the bracket. We'll just do the right side of the bracket with the a and the b there. And what that notation is telling us to do is it's telling us to evaluate the antiderivative at the upper limit, b, and then evaluate the antiderivative at the lower limit, a, and subtract them, and that will give us the area. Okay? So all that limit of the sum stuff is summed up right here by just doing capital F of b minus capital F of a. Okay? Now, a couple reasons why we can use the antiderivative. You'll notice I skipped a line in there that had the c. Okay? The c is not necessary because if you notice, when we do this subtraction, the c would be the same for both the antiderivatives. So c minus the c will cancel itself out. Okay, it won't matter. We are left with just f of b minus f of a. So let's examine how this works. Alright, first of all, and I'm going to show more work than I typically would for the first example or two here, but I want you to make the connection with the notation. So here the function that we're dealing with is this quadratic 3x squared plus 2. Okay? So what is the antiderivative?
3x cubed over 3.
Okay, we got a 3x cubed over 3 plus 2x. Alright, and that just simplifies to x cubed plus 2x.
Plus c.
Plus the c. Okay? Plus the c. So, when we are doing the definite integral from -1 to 2, this is what we're going to do. We're going to do that x cubed plus 2x. I don't need to bother writing the c. And I'm going to go from -1 to 2. So what I'm doing here is, first of all, I plug in 2. I have 2 cubed plus 2 times 2. And then I subtract a -1 cubed plus 2 times -1. Okay? So, we have here 8 plus 4 is 12, minus -1 minus 2 is a -3, so 12 plus 3 would be 15.
And that's it.
And that's it. If you remember, that's the warm-up problem we did yesterday. Okay?
Oh.
You guys did the limit of the sum, and it took us like,
Yeah.
you know,
Yeah.
7 or 8 minutes. Yeah. So now you're done in a minute or two. Okay? Yeah, so that's really nice. But let's look at what's actually happening here. I want you guys to understand what we're actually finding. Okay? If I were to sketch this, the quadratic 3x squared plus 2 It's hitting up here at 2. 3x squared. So over at positive 2, I would be at 3 times 4 is 12. That's 14. Okay. This picture ought to look familiar. At negative 1, I'm going to be at 5. Okay. So it looked like this. Okay. What is happening geometrically is when I do that capital F of 2, the capital F of 2 is actually giving me this area right here. Okay? It gives me the area under the curve from 2 all the way to the left until I get to the y-axis. Okay? When I do capital F of negative 1, it's actually giving me this. Capital F of negative 1 is that. Notice we ended up being negative 3. That's because it's to the left of the y-axis. Okay? So it's negative. When we subtract, notice what gets added together. The 12 in the red and the 3 on the left get added together, and I have a total of an area of 15. Okay? That's what's happening geometrically when we're doing the fundamental theorem of calculus. Okay? So this was a negative 3. Over here is a 12. And you do 12 minus the negative 3. Okay? And I might say, well, why do we subtract? Well, let's take a look at another example, and you'll see, I'll illustrate that one as well, and I think it'll be more clear why we subtract. So here we have the integral of 3 root x. You do not need to draw all of these, I'm just doing it for your own observation. Okay? So at 1, square root of 1 is 1 times 3 is 3. At 4, 2, 3, 4. There's 1 to 4. Square root of 4 is 2 times 3 is 6. Okay, so here's the point 4, 6. Here's the point 1, 3. This graph looks like this. Okay. When I go to do the integral, let's go ahead and do that antiderivative now. F of x is 3, and I'll put it as x to the 1/2 power. What is our capital F of x here?
2x to 3 over 2.
Okay, you add 1 to the exponent, it's x to the 3 over 2. And then you divide by the 3/2, which is the same as multiplying by 2/3. Flip and multiply. Okay, so very good. The 3's cancel out. Capital F of x is 2x to the 3/2 power. There is a plus c, but we're not going to use it in the definite integral. Okay? So, we have here 2x to the 3/2 that we are going to evaluate from 1 to 4. So if I plug in 4, it's 2 times, and I'm going to put the radicals in now, square root of 4 cubed. That's what the 3/2 power is. Alright, and that part equals 2 times 8, so 16. Now, what we just found here was this area right here, all the way over to 0, or all the way over to the y-axis. That is the capital F of 4, and that is 16. The problem is we included too much area, and this is why fundamental theorem of calculus says we need to now subtract the capital F of 1. Okay? So it's 2 times the square root of 1 cubed, so that's minus 2. On the graph here, that 2 is this extra piece to the left of 1 that we didn't want. That's why we're doing the subtracting, okay? It wasn't quite as clear as the first one because we were over to the left. But here, capital F of 1 is 2. So we subtract that extra bit, okay? Does that make sense? Okay. You don't have to draw all these, although it might be helpful in some cases for you. The main thing here is getting your antiderivative, plug in the upper limit, plug in the lower limit, and subtract. Okay. Here's one you may have to think about a little bit. What's the antiderivative of secant squared x? What is it?
Tangent secant. I don't even know which one.
Someone said the right answer. Huh? It's just tangent of x. Remember with the trig functions, think about, okay, what had a derivative equal to secant squared? And that's the derivative of tangent is secant squared. Okay? So capital F of x is tan x plus c. So what we're going to be doing here is taking tangent of x and evaluating it from 0 to pi over 4. Okay? Always do the upper limit first. So we have tangent of pi over 4 minus the tangent of 0. What's the tangent of pi over 4?
1.
It's 1. Good. And tangent of 0 is?
0.
0. So this is 1. Okay? That's not too bad, huh?
No.
That's a whole lot better than doing limits and sums, isn't it? All right. So yeah, so that is our fundamental theorem of calculus. That's really all there is to it, at least the first part here. We will look at the second fundamental theorem of calculus later on. But we got some other practice that we can do with this as well, okay? And notice the different ways that you can write the problem as well, okay? So let's look at application number 1. What do we do when we see absolute value? Rewrite it as a piecewise, okay? So, here I have the integral from 0 to 2, okay? But my function, 2x minus 1, it might be helpful to actually see this. 2x minus 1 would have a y-intercept at -1, a slope of plus 2 over 1. Okay? So the line would look like this without the absolute value. With the absolute value, right here it's going to bounce back up. So that's the absolute value that we're looking for. Where does it hit that x-axis? At 1/2. Okay, half of 2 is 1 minus 1 is 0. Okay, so when I'm doing the piecewise function here, it's gonna be the line 2x minus 1, but only after I hit x equals 1/2. It's going to be negative 2x plus 1 when x has yet to reach 1/2. And again, it doesn't matter in this case whether you put the equals with the first one or the second one, just don't put it with both.
You have to put greater than or equal to 0.
It actually, for the function itself, it doesn't matter. Because the function is defined for all real numbers. The 0 comes in when we actually do the integral, okay? So here, this is a case where we're going to need, well, how are we going to do this? If we got to go from a half over here to 2, or I'm sorry, we got to go from 0 over to 2, what are we going to do with the integrals?
You do 2x minus 1.
Add
2.
what?
From 0 to half and half to 2.
There we go. We're going to have to separate this into two different integrals. Okay? And we're going to have to do the integral from 0 to a half of the negative 2x plus 1 dx. And we're going to add to that the integral from a half to 2 of positive 2x minus 1 dx. Okay? So now we're doing the fundamental theorem of calculus twice. Okay? The first half, what's the antiderivative?
Negative 2x squared over 2 plus x.
So negative x squared plus x.
Okay, so negative 2x squared over 2, which is just a negative x squared, plus x. We're going to evaluate that from 0 to a half. Okay, and excuse me. When I plug in a half, what do I get?
Negative 1/2 squared plus 1/2.
Okay, negative a half squared, so negative,
1/4.
oh yeah, this should be an x. So negative 1/4 plus a half, that's evaluated at a half. And then I got to subtract it. What is it when it's evaluated at 0? 0. Okay?
So 1/4 minus 0.
So this is 1/4, but that's only half the problem, right? I need to go back now and add the other integral. Okay? So that's all half of it. So now here, again, take the antiderivative. 2x squared over 2, or just x squared, and this time it's positive. But then I do minus x. And I evaluate that from a half to 2. Okay? Always do the upper limit first. So when I plug in 2, I've got a 4 minus 2. And then I subtract. What do I get when I plug in a half?
1/4 minus a half.
1/4 minus a half. Okay. So I get 2.
Plus a fourth.
Yeah, 2 plus a fourth. So 2 1/4. So total, this integral would be 2 1/2. Okay?
Mr.
Yes.
How do you know that the absolute value function looks like that? Wouldn't it look kind of like this view here, just down and up?
It is. What I did first is, if anytime you draw sketch an absolute value, what I usually will do is I will simply sketch it as though there weren't an absolute value. If the entire thing is an absolute value, I should say. I just sketched the line, and then where it started to go negative, it reflects up. It's a little bit different if you've got like
Okay.
a +4 on the outside of the absolute value or something like that. But
And that second part will hit the y-axis at -1, it's just not included in the function.
Yeah, that, this part here is not part of our actual function, it's just what I use to help me sketch it.
Understand.
Yes.
So we're gonna have to be able to sketch on our own without using a graph.
Yeah, you should be able to sketch absolute value functions. So, okay, by the way, we can double check our answers. These are both little triangles, right? So this has a base of 1/2 and a height of 1, so the area there was 1/4, 1/2 base times height. This one has a base of 1.5 and a height, if I plug in 2, I get 4 minus 1, 3. So the height there, or the area there, 1/2 base times height, would be 1/2 times 3 is 1.5 times 1.5 is 2 1/4. So you add them together and you get 2.5. Okay. So that kind of just confirms what we did with the integral. Okay. All right. So then we have this. It says find the area of the region bounded by the graph of y equals 2x squared minus 3x plus 2, the x-axis, and the vertical lines x equals 0 and x equals 2. So let me go ahead and draw those vertical lines. Here's the vertical line x equals 2, and here's x equals 0. So the area that we're trying to find here is this whole area in here. Now it does say area enclosed, or area of the region bounded. So if this had gone below the x-axis, I would make that area positive. Okay, because it says the area bounded. It doesn't just say get the integral here. Okay?
It's like total area from, yes.
Yeah, if it's total area, or if it's asking for area bounded, anything that went underneath and was negative, we would make positive. Okay? In this case, it's a non-issue, but I wanted to mention that again. So, what's the problem really asking us to do? What should we set up?
The integral from 0 to 2 of that function.
The integral from 0 to 2 of that function. Try doing this one on your own, okay? You guys know how to find the antiderivative. Go ahead and try using the fundamental theorem of calculus. We'll see how you do with it. Alright guys, what did you get for the antiderivative here?
2x cubed over 3.
2x cubed over 3?
Minus 3x squared over 2.
Okay.
Plus 2x.
Plus 2x. Okay. Now, when you evaluate this for 2,
It was
what do you get?
10 over 3.
10 over 3? Okay. You have 16 thirds minus, if you do that, 2 squared is 4 over 2 is 2, so that's 6. So if we get a common denominator, that'll be 18 thirds. Yeah, plus 4, which is 12 thirds. Getting a common denominator can be helpful there. And then if I put all that together, I get negative 2 plus 12 is 10 thirds. Okay? Now, what do you get? That's all the capital F of 2. What do I get when I plug in 0? 0. Okay, that's nice. Alright, so the whole thing, the area there is just 10 thirds.